Welcome back for our last talk today. We're happy to have Jérémie Chalopin, who will tell us about graphs with convex balls.
Okay, thank you for giving me the opportunity to talk here. So first thing I have to say is that I don't do a geometric group theory, I do a graph theory. So I will mainly talk about graphs and at the end a bit about groups. If you have any questions, please feel free to ask. So this is a joint work with Victor Chepoi, who's a colleague of mine, he's also in Marseille, and Hugo Giocanti, who was a master's student, now is doing a PhD in Grenoble. So we are talking about graphs and about convexity in graphs. So here's the first proof I'm not a geometric group theorist. For me, G is a graph, not a group. So we are looking about graphs. So for the talk, we will assume they're locally finite. Most of the results, they will all without this, but in any case, what we should avoid is a infinite click, so infinite complete graph, because it will be a mess. And we look at the graph and as a metric space where the distance is the standard graph distance. And as in we have learned last week, we are looking at convexity. So important notion is the notion of an interval. So the interval between two vertices is the set of vertices that lie on a shorter space. So if I take these two guys, the two dark blue vertices, all the light blue ones are in the intervals because they belong to a shorter space between them. And we said that the set is convex if for any two vertices in the set, the interval between them is also in the set. So this interval is convex. And for example, this is not the set of blue vertices is not convex because there is this vertex that belongs to this shorter space, and that is not in the interval between the two guys. Okay. So I will talk about so what we did, it was about graphs with convex balls, but in the talk I will talk both about bridge graphs and graphs with convex balls because they have been historically introduced at the same time. Bridge graphs, they got a lot of attention since then. Graph with convex ball, much less, but I want to show the fact that we have a similar kind of results for both. So a graph is a bridge graph. So bridge graphs correspond to systolic complexes, but initially it was introduced by people in metric graph theory. So independently by Soltan and Chepoi and then Farber and Jamison. And we said that the graph is bridged whenever you take a convex set, if you look at the neighborhood of a convex set, it's still convex. So this is something. So all these things, when they introduced this, it was they were looking at metric properties that were true in, for example, in the Euclidean space, and they were saying, okay, now we play with graphs. What can we say about this? And the graph with a convex ball is a graph where we don't look at neighborhoods of any convex set, but we look at balls in the graph. So the property we have is that a graph is a bridge. If a graph is bridged, then it has convex balls. But we will see that it's not equivalent in the setting of graphs. Okay, so these are a few examples. So first example, trees. So the first row is graphs that are bridged. The second row is graphs that have convex balls but are not bridged. So trees are graphs that are bridged. If you take the triangulation of the plane, you'll have a bridge graph. And globally, I think you know that if you look at a graph where if you look at in the link of each vertex, you have no 4 cycles or 5 cycles. So either you can have triangles because it will give you simplices, but you can have large cycles, but you cannot have cycles of length 4 and 5. Then you get a bridge graph. And the things we can add when we have convex balls. So all these graphs, they also have convex balls. But for example, we can have pentagons now. So here are 3 graphs that have pentagons that have convex balls, but they are not bridged. So we'll come back on examples later. So these are the this is the classical Peterson graph that is a favorite graph of many people in graph theory. Another example is the Hoffman singleton graph. So in fact, what we can observe is that if you take a graph where you don't have cycle of length 4. So when I say you don't have a cycle, it means you don't have so what we call induced cycle, so what you call full cycle. So it means that if you look at the graph, you don't have a cycle of length 4, but you can have a cycle of length 4 with a diagonal. This is okay. If you have a graph that doesn't have cycle of length 4 and its diameter is 2, then automatically it will have convex balls. It will not be necessarily bridged, but it will be will have convex balls. And this is such an example, and this is the largest graph with convex balls that does not have triangle that we know. Possibly there is another one, but we don't know if it exists. Okay, so the initial work of Soltan and Chepoi and Farber and Jamison, it was to characterize these graphs from a metric point of view. So the first thing we can look at is a cycle. So it's quite easy to see that if you have a cycle, you will not have convex balls except if you are a cycle of length 3 or 5. So if you have an even cycle, if you look at the ball centered here, and you take so here it's n is 3, so you have C6. So if you take a ball of radius n-1, then you have these 2 vertices, but you don't have the opposite vertex of this one. But the only shortest path between these 2 vertices is this one, so you have a problem. So it means you cannot have a cycle of even length, even a cycle of length 4. If you have a cycle of odd length, you can do the same. And if the size of the cycle is at least 7, then the distance between these 2 vertices is the distance outside of the ball. So it's not, it means that the shortest path between these two vertices is not in the ball, so the balls are not convex. And for bridge graphs, so cycle of length 5, it's okay for a convex ball, because if, for example, if I take this vertex, I can look at the ball of radius 1, but then this path is of length 3, but I don't care because the distance in the graph is 2. So the cycle of length 5, it has convex balls. But it's not bridged because an edge is a convex set. I can look at its neighborhood, and I have these 4 vertices, and again, I have a problem. And in fact, this this study of cycle, it's enough to characterize bridge graphs. So the result of Soltan and Chepoi and Farber and Jamison, it was that graph is bridged if and only if every isometric cycle is of length 3. So isometric cycle, it means that you take a cycle and the distance between 2 vertices of the cycle in the graph is the same as in the cycle. So if you have a cycle with a shortcut, so for example, here I had a cycle of length 6, but it is not isometric because the distance between these 2 vertices is 2 and not 3. And so a graph is bridged if and only if every isometric cycle is of length 3. And the graph is a graph with convex ball. So every isometric cycle has to be of length 3 and 5, or 5. But it's not enough. And so the graph should also satisfy what we call the interval neighborhood condition. So what does it say? Say that if you take 2 vertices U and V, and if you can go from U to V through a vertex X and a vertex Y, so both X and Y are in the interval between U and V, and they are adjacent to U, then X and Y should be adjacent. So it will put a lot of triangles in your graphs.
You wrote that does not have convex ball, A equal to 4, return equal to 10, but what about 6?
6 is okay. No, wait. No, 6. No. Sorry. It's 6. It should be 6. No, sorry. It should be 6. Okay, and so these were the two initial characterization of a graph with convex balls and bridge graphs. So we can look at other properties that are satisfied by this graph. So I will look at metric property. So a bridge graph, it satisfies the triangle condition. So what does it say? It says that if you have two vertices V and W that are at the same distance from a vertex U, then you can always find a common neighbor of V and W to go towards you. So there is a triangle. You can find a vertex X such that you will have a triangle and you will be closer, one step closer to you. So this is this condition plus the quadrangle condition. It defines what is called a weakly modular graph. That's a very, very large class of graph. So it's no longer true for a graph with convex ball, because if you take a pentagon, you don't have the property. But what we showed is that you have what we call the triangle-pentagon condition. So in exactly the same situation, either you have a triangle, or if you don't have a triangle, you can find a pentagon. So you can find Y and Z that are neighbors on V and W at distance k-1, and X, a common neighbor of Y and Z, that will be one step closer again to you. And so the result, so Chepoi showed that graph is bridged if it satisfies this interval neighborhood condition. That in the interval you should have a triangle. So in fact, here I just put it for two vertices, but it also means that all neighbors of U in the interval between U and V, they should form a complete graph, a clique. If X and Y are in the interval between U and V and are adjacent to U, they should be connected. So it means that if you look at all the neighbors of U that are closer than V, than U, they should form a clique. And in fact, they will even form. So the result of so it was not stated exactly like this. It was a bit different, but from its result, you get this. You get that it's a graph is bridged if it satisfies the interval neighborhood condition, triangle condition, and you should not have any cycle of length 5. And what we showed is that the graph is a CB graph, a graph with convex balls, if it satisfies the interval neighborhood condition and the triangle pentagon condition. So here there is something natural to ask is that if we remove what if we remove this? And in fact, the class of a weakly bridge graph or weakly systolic graphs that Damien introduced with Victor, they show that they are. So again, it's not like this. It's about weak modularity, the result, but it will be exactly the graph that satisfies the interval neighborhood condition and the triangle condition. So we have, it's this characterization. There are still metric characterization. We are still talking about distances and things like that. But in some sense, there is one vertex that is far away, but the other vertices implied in the conditions are in a small ball. So this is a kind of things we like because to do the proofs, it's much easier than to handle cycles that can be anywhere in the graph. And so the result, okay. One important result of Victor, he showed that the graph is bridged if and only if its triangle complex is simply connected, and you don't have W4 and W5. So it means, so W4 is this graph, W5 is this graph. It means that in the link of a vertex, you don't have cycle of length 4, cycle of length 5. So the standard way for us to define, we work with graphs. So when we need to do to take a complex, we take our graph, and if we see a triangle, we put a triangle. We don't think too much. And this characterization, in fact, is I don't know, usual definition of systolic complexes that have been reintroduced later geometric group theory.
I didn't actually. It's Haglund and Chepoi. I heard about it from Janskevich, and then I wrote my own beautiful, amazing paper about it.
Okay. 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 So then Victor and Damian. No. Okay. When I say you have no cycle, no W4, no W5, I mean you cannot have this graph as an induced graph. So it means that you can have an edge. Yes, thank you. So Damian and Victor, they show that the graph is weakly bridged if you forbid the cycle of length 4. And you have a simply connected triangle complex, and you have this extra condition that is called W5 hat condition. And what does it say? It says that if you have this, so this is so it's W4, W5 is because it's called wheel. So this is a wheel on 5 vertices. And if you glue a triangle on one side, then so it's clear that this cannot be an isometric subgraph of your graph, because these two vertices, they are at distance 2 from this one, and this one is at distance 3. So if this, well, it cannot be isometric. Like if this distance is 3, these two should be adjacent, so it's not possible. But so this distance should be at most 2. But in fact, what they ask is that the condition, it says that if you have such a configuration, then there should be a vertex. It should be in the link of someone. There should be a vertex that is adjacent to everyone. So if you have this local condition plus no cycle of length 4, then you get a weakly bridged graph. And our result is that you have a graph with convex ball if the small balls are convex, so balls of radius at most 3 are convex, and the triangle-pentagon complex is simply connected. So the thing is that now we don't have only, before it was kind of nice because you can just take the triangle, all triangles as your two-dimensional faces, and you get something simply connected. But since now we have a cycle of length 5 that cannot be filled, so what we do is that, okay, we say that the two-dimensional cells are all triangles and all pentagons. If we see a cycle of length 5, we don't care. So again, without any chords, we don't care whether it's in a W5 or not. We put a face. So the main difficulty in the proof, so it's that we have to handle two kinds of cells, triangle and pentagon. So in fact, we don't really try this time. We didn't really try to do a proof via these diagrams. So the original proof for bridge graphs of Victor, it was based on minimal area disk diagrams, and you can reduce the area, and so it's a very nice proof using Gauss Bonnet. But here, the fact that you have two different kinds of cells, it's a mess. And we had some paper with Victor and Damian and others about graphs with triangle square complexes. So it was already a bit more difficult, but the fact that we have pentagons, it makes the proof much more. So the general strategy is the same, but it's much more involved. So instead of using these diagrams, what we do is we start from a graph that is where the small balls are convex, and we will try to build its universal cover inductively. And this is what we have done previously for Lie graphs or weakly modular graphs. So I want to, okay, I will try to give some ideas of the proof. I will not go into details. So there is one direction that is quite easy. Like if you're a CB graph, okay, if you have a graph with convex balls, your small balls are convex, and to show that the triangle-pentagon complex is simply connected, it's very easy, and it's where it's useful to have this triangle-pentagon condition. Because what you do is you take any cycle you want in your graph, and you want to show that you can contract it to a point. So suppose that since your graph with convex ball, you satisfy these two conditions. And so in the drawing, you should imagine that vertices on the same level, they are the same distance from V. So what you say, okay, I look at the vertices that are the further away from V. And what I will do is that if we can do an induction and okay, this maximum, then the number of vertices at the maximum distance, and then the number of edges at maximum distance. So either you have a vertex at maximum distance so that its two neighbors are closer to V. Then by the interval neighborhood condition, we know that there is this edge, so we can replace this cycle by a cycle that is closer. And if you have an edge, if you are not in this case, that it means you have an edge at maximum distance. Then you can apply either the triangle condition or the pentagon condition. And again, you can reduce. So you will not reduce the number of vertices at maximum distance, but you will reduce the number of edges at maximum distance. So if you do this, you can contract your cycle via triangles and pentagon to your vertex, to your base point. Okay, this was the easy way. In the other direction, what we do is that we take a vertex V, and for each vertex V, what we will do is we will construct we will construct a cover that will satisfy the interval neighborhood condition and the triangle pentagon condition. So from this, what we will get is that from the previous slide, we will get that this will be simply connected. So this will be the universal cover of our initial complex. And so it means that it will be for all vertices, it will be the same complex. So it will mean, and it will be X. So it means that the graph, the initial graph we have is in fact isomorphic to the one skeleton of the universal cover. And so since the one skeleton of the universal cover will satisfy our two conditions, our graph will also satisfy them, and thus we will get that our graph is a graph with convex balls. And the way we do it is by induction. We start with one vertex, and we will construct vertices at distance, first at distance 1, then 2, etc. And the inductive arguments are a bit natural. So the first thing is that at each step, if I'm not, so BI, it will be the ball of radius I around my base point. And at each step, I will add vertices at distance I plus 1. And so if, okay, this is not very good. Okay, this is not completely true. Well, so, okay, like this, it's true, but not, I should have written something else. What we'll have is that locally, I will have a bijection between the vertices. If I take a vertex that is not on the last layer, I will have bijection, an isomorphism between the links of a vertex and the link of its image. If I'm on the border, I will not have it will not be bijective because I may still miss some vertices, but I will have isomorphism between the image of my ball and I will have an isomorphism between the ball around the vertex W tilde and its image around W. No, and its image. So it means the image of this, for example, the image of these two triangles or these two triangles So I may miss something, but if these two are adjacent, these two have to be adjacent, if and only if. Okay, so this is just the way we will build it, and then we will say that we will take care to build the graph in such a way that we will always preserve these two properties, the interval neighborhood condition, with respect to the initial vertex. So it means that if we have two vertices at distance I-1 and a vertex at distance adjacent to a common vertex at distance I, these two have to be adjacent. And the triangle pentagon, it says that if I have an edge that is with two vertices at the same distance, either I have a triangle or I have a pentagon. And the difficult property to establish, in fact, we don't really need it, but we need it to prove everything else, is that if you have a path of length 5 in your graph, in the graph we are constructing, then if the image of these two vertices are adjacent in the initial graph, then there should be adjacent. Okay, and this I will not talk about, but this is what makes the proof difficult. Okay, so we start with a ball of radius 1 around the vertex. And then the strategy we use is something a bit similar to what has been done before. You look at the guys on the last layer and you say, okay, I want to build the covering, so I should have the good neighbors. So I look, what are the neighbors I'm missing? So for each vertex W tilde in the graph I construct, I look at all neighbors of its image, so that such that no vertex, no neighbor of W tilde is mapped to. So I look at all Z that are neighbor of W, such that no neighbor of W tilde is mapped to Z. And I say, okay, this I want to add a neighbor for each such. So this we can call a germ. For each such germ, I want to have a neighbor in the next step for W tilde. And the thing is that we need to define some equivalence relation between these two, between this set of germs. And in this case, it's quite easy. We just say that if I have an edge between two, if I have two adjacent vertices that have two germs with the same Z, and if these two, well, if their images are both adjacent to Z, then I say that these two vertices are in a relation. In fact, what we have a bit, we have something stronger. We can show that if we have such a relation, then we know that we can find a vertex U tilde that will be closer to V and adjacent to both W and W prime. And what makes everything work is that this is an equivalence relation. So if I have this, then I can build the next level of my graph. What I will do, I will just add a vertex for each equivalence class of this relation. And I will connect W tilde with all the equivalence class of all W tilde Z that exist. So this defines like the vertical edges, so edges between vertices at distance I and vertices at distance I+1. But now I also have to define horizontal edges. So if I have two vertices that are two germs from the same vertex, such that these two, the corresponding Z and Z prime are adjacent, then I will put an edge. And if I have something like this, so it means that I have a vertex U tilde that is adjacent to W and W prime that is closer to V than both of them. And if Z, Z prime, W prime, U, and W is a cycle of length 5, induced cycle of length 5 in my graph, then I will put an edge here between these two germs. So this is the way we construct the graph. And in fact, if you look, how we define the. So here, when I did this, I ensure that if I added, here I will add one vertex that will be adjacent to W and to W prime. But when I do this, there will always be an edge between these two. So it means I will automatically have this interval neighborhood condition with respect to my base points. And the way we define edges is the same. If I put an horizontal edge, I know that there is a triangle in my graph or a pentagon. So I have the interval neighborhood and triangle pentagon condition completely for free. The hard part is to show that that all the other property hold, and that we can do really the induction. And okay, so then we take the directed union of everything, and we get that the graph we constructed is the one skeleton of the universal cover of our initial graph. So we get that our graph is a CB graph because it satisfies. It is simply because it satisfies the interval neighborhood condition and the triangle pentagon condition.
Properties are being localized. Say that it's easy to say that.
And the other, there is nothing very difficult. The only so you want to have a local isomorphism, and in fact, so what I didn't really say is that since you have pentagons as two-dimensional cells, you have to take care that you really have bijection between the stars, isomorphism between the stars. In the inductive condition I said, I was just talking about really the one neighborhood, and then we have to do extra work for the stars, and this is this property that 5 cycles are preserved in a good way. That is hard to prove it's why it's used. But the fact that you have bijection between neighbors, it's also quite easy by construction. It's more like the fact that for cells like triangles and pentagons are preserved that is more difficult. Okay, so this was a local to global result. So so we have other result that are in the spirit of what exists for bridged and weakly bridged graphs. So so Anstey and Farber, they showed that bridge graphs are dismantlable. So it was Nima told us about this last week. I will explain just after what it means. But if you have a locally finite graph, if you are dismantlable, it implies that your clique complex is contractible. And just something I wanted to say is that that both proofs, not both proofs, this proof, and there is another proof of this by Chepoi, they are very algorithmic. Like you do a breadth first search in your graph and you get something like this. So because I'm not in the math department in Marseille, I'm in the computer science department. So for us, we like to do algorithms. So we say that the graph is dismantlable. So if you have an ordering on all your vertices, and with the property that if you for any vertex I, if you look at all the vertices that have been labeled before I, so this is GI, the VI and its neighborhood, they are included in the neighborhood of another vertex. So, for example, if we look here, if we look at so this as the vertex 6, its neighborhood is V6, V5, V3. So it's included, for example, in the neighborhood of V5. There is someone, it's included in the neighborhood of someone that is labeled before it. So in some sense, it means, okay, I can remove the vertex from my graph. And I can start again. V5, its neighborhood is included in the one neighborhood of 2. So I can remove V5. Then I can remove V4 because it's included, etc. And if you can, so this is for if you start from a finite graph, it means you can start really deconstruct your graph until you arrive to a point. But if you do it in the other direction, it means you can construct your graph, even if it's infinite, you have something that is natural. So graphs that are dismantlable, you have trees, cliques, chordal graphs, or heli graphs, many graph classes. And the thing is that now we are working with a triangle and pentagon in our graphs. So a pentagon, it's not dismantlable. But, and it will not, the clique complex of the pentagon, it will not be contractible. So there is one thing we cannot do, we don't know how to do. We don't know how to find like cell complex with a higher dimensional cell such that the two complex is precisely the triangle pentagon complex we were having. But what we do is we can look at what we called the square of a graph. So it means you take your graph, you keep the same vertices, and you put an edge if the distance between two vertices is at most 2. So it means that each time you had two, you take your graph and you had all edges between vertices at distance 2. And the property we have is that we show that any breadth first search order, so it means I don't know, you start from a vertex, and what you do is that you have a list of priority. When you consider a vertex, you look at all its neighbors and you put them at the end of the list. And the next vertex you label is the first one in the list. And it will give you a dismantling order for the square of the graph. And so it means that the clique complex of the square of the graph is contractible. So it means you can find some contractible complex for your graph with convex ball, and the definition is this complex. It's a very natural definition. It's very, so if you have some symmetries, you will keep all the symmetries. Okay, so the proof is not very difficult, but it's just there are many cases. It's not so interesting, I think, for you. And the last thing I wanted to talk about is bioautomaticity. So, okay, so so since we have graphs, we can say, okay, now I look at group acting on this graph. So this I don't know much, but we said that a group is systolic if you have geometric action on a bridge graph or on the associated systolic complex. And you do the same for weakly systolic or for a CB group. And there is a result by Januszkiewicz and Chatkowski that systolic groups are biautomatic. And in some sense, we extended their proof. So again, we have pentagons, so it's a bit more technical, but we show that groups, yes. So I don't have any example, but Damian has example of weakly systolic groups that are not systolic, I think. And we don't have an example. This is a question at the end. It's a question for you because we looked at the graphs, and then since there were these results about groups, we get them, but we don't know if we really get something new in terms of groups. And our proof is similar, in fact, to this one. So the thing is that okay, what is a nice thing is a nice result by Shankowski that said that to prove that some group is bioautomatic, you can work only with graphs. So you don't really need to understand groups again. You can just understand graphs, and for us, it's good. So if you have a group that acts on the vertices of a graph, you say that a path system, it's a set of paths such that it's stable. If you apply any automorphism of the group, you stay in the same set. And it's locally recognized if, for any path, it will be in your family, if and only if any subpath of length at most k will be in your family. So it means that you have some finite properties that if you check locally that everything is okay, then it will be globally okay. And so to show that a group acting geometrically on a graph is biautomatic, it's enough to find such a path system that will be locally recognized, that will be any two vertices in the orbit of some vertex V0 will be connected by a path, and you want that your set of paths satisfies the two-sided fellow traveler property. So this is okay, this is the definition, but this is what we use. In fact, it says that if you take two edges in your graph and you take two paths, so you take okay. So it's the same as proving these two properties. So if I take the paths, the way we define them, they are not symmetric. So like there are paths from U to V and there are paths from V to U, but there is no reason that a path from U to V, if you reverse it, it belongs to your family. It says that if you take a path that goes from U to V and a path that goes from U to V prime, if these two vertices are close enough, then these two paths, they stay at bounded distance. And the same in the other direction. If you have a path from U to V and a path from U prime to V, then they stay at bounded distance. And this is, okay, so what we want to do is to define a set of paths. So we take two vertices U and V at distance k. And so we start in V. So what we will define is a set of cliques, because we cannot really define the path in the graph. We'll have to work in some other graph. But we will define a set of cliques within the graph, that is what we call the clique path. So you start from V. And then what you say is you say, okay, I want to go toward you. So I take all vertices that are on a shortest path from V to U. So the first step, it's easy. Now you want to do the same with the property. Now you don't have only one vertex, you have a clique. So what you say is that I want to take a vertex that such that I can go towards you for all vertices in my clique. So I take, so this is what is written here. I take okay, here there should be an I. I take the intersection of all ball of radius 1 of the vertices here, and I intersect with the ball of radius I minus 1 because I want to get closer. And the fact that this vertex exists, it's because it just by this interval neighborhood condition gives you that here you have a clique. And the fact that here you have a vertex, it's because you have a clique plus a vertex a bit further away, at least one. And so again, you get a clique. And you do this like this, and you get a set of cliques in your graph. So this is a set of paths that we understand, because it's like it gives you kind of geodesics in your graph. It's not, except it's not vertices, it's clique. It's okay. But now we have to show that so okay, the property is that it is well defined. Each time it's not an empty, and each time it's a clique. And the thing is that we have to get some local to global property. Because to have this locally recognized, we need to show that if you take such a long path, you can have criterion that will be a local criterion that will ensure that you're in the set. So we said that a clique path is normal clique path. You have a set of cliques, and these are the conditions. I don't have pictures. Not good. What does it say? It says that if I take two consecutive cliques, I should have a complete subgraph, a complete graph between them. So the union of two consecutive cliques is a clique. But if I take two cliques at distance 2, they should. Oh wait. Okay, no. First, my cliques they do not intersect. This this and this, they say that two neighboring clicks, they do not intersect, but together they form a click. Two clicks at distance with a difference of index of 2, they do not intersect, but they do not see each other. So they are what we call that uniform distance 2. So if you take any vertex in a ci-1 and any vertex in ci+1, the distance should be 2. And here, this is something that was not in the case for in the systolic case. We have to say that if you take clicks at distance 3, so ci and ci-3, the distance between them should be 3. And then, before I was saying to define ci, wait, okay. To define ci, I was thinking, okay, I take all the vertices that are in all balls centered at the vertices of ci+1, and I was saying that are closer from U, from C0. But here I just say, okay, I say that are neighbor of someone in ci-1. So if I do this, if I look at this condition, these conditions are very local. It just talk about in my path of clicks that are at distance at most 3. And what we show is that for any vertices UV, the click path I defined on the previous slide is the unique normal click path from U to V. So it means we have kind of a local recognizability. Okay, and okay, I will not do the proof, but we want to show these two properties. In fact, since we have the triangle-pentagon condition, we can even assume that, like for example, if I go from U to V, I can go through V prime, and the same on the other side. So there is one direction. This direction is easy, and this one is hard. It's harder. Okay, and so if we really want to apply the theorem of Jankowski, we have to define some actions on the graph. So instead of looking at the action on the graph, we look at the action of our groups on the barycentric subdivision. But we get normal click paths. That the normal click paths, they will give us a locally recognized path system in the barycentric subdivision of our graph, and they will follow travel. And so we will get the arebiautomaticity result. And so the I don't know, the conclusion or the general idea is that in a graph with convex balls and CB groups, everything behaves similarly as in a weakly systolic graph, but everything is a bit more complicated when you have to do a proof. But globally, we don't. We have other results, like metric results, that show that it's very local differences. But the real question, that is a question of Thomas, is that we don't know if there is any group that the CB in this new class that is not weakly systolic. For graphs, we have plenty of examples. We understand a bit, but for groups, we have no idea. And okay, we stop here. Thank you.
What do you say about diameter, maximal diameter of graphs, CB graphs?
If you take a CB graph without triangles, it's necessary its diameter is at most 2, because if you have a no, wait, sorry. If you take a CB graph, either you have a cut vertex, so you can there is a vertex. If you remove it, you disconnect your graph, or you have a triangle, or your diameter is at most 2. Because if you have two vertices at distance 3, since there is no cut vertex, I should have at least two paths starting from here. So then I will have an edge, so I will have a triangle. And so these graphs, in fact, there are only 5 or 4, I don't know. So graphs of diameter 2 with convex balls without triangles there is this one, and potentially there is a graph, so more graph on 50. So graph, I don't remember the number of vertices, the degrees 57 or something like this. Because they have been studied as it's a graph of diameter 2 and girth 5, like minimal. So, and we know that we have only a finite family. But you can have graphs of diameter 2 with triangle that are complicated. And we have a result that is not well written. So we can also, if you take, so the thing, okay, I'm not completely sure what we have written, but if you have a finite graph, it's okay. I think it works also for, if you have a finite graph and you take one automorphism of your finite CB graph, you will fix something, but what you will fix is something of diameter 2. It's a convex set of diameter 2. But we cannot ensure it's a clique, we cannot ensure it's a clique or a cycle of length 5. We don't really understand how complicated it can be. But globally, you have something small.
Yes, that maybe convex subgraphs of diameter 2 are itself.
Yes, maybe, because this is what will be fixed. But
That's something that
we didn't. But no, we didn't look in details. Not clear how large it can be, but yeah, we should look. Yeah.
Beginning with C3 in the systolic or E, but it's not systolic.
I don't know.
In the proof of local to global,
Yes.
like I've seen the proof, the same theorem for weakly modular.
Yes.
Sort of the same strategy.
Yes.
We built the
Unit. Yeah.
layer by layer. When you define a graph by some local conditions, like either on lengths or like banished small subgraphs, when can you expect to have this ability to build up a layer?
My intuition of this is that you need to have this kind of if you have this kind of characterization is good, because this kind of characterization, it tells you if I have some vertex that can be far away, plus some guys that are nearby, then I expect to have something more. And what we did, like, we want to prove by induction that if we add layers by layers vertices, we have the property. And this is exactly what you want, because you're at each step, you're just controlling the last vertices you add at this step. So you don't want that if these guys interact with someone that has been defined a long time ago. And if you look at the proof for here, for weakly modular, for Heli, for Bucoli, all our proofs, we have hidden some, not necessarily hidden, but the characterization we start with, not we start with, but the characterization we use to prove the result is something like this. Like, for example, if I wanted to prove this with a cycle, only for bridge graph is the only isometric cycles of our length 3, then I don't know how we would.
Is there like a lurking meta theorem?
Not really, because each time, I mean, the strategy is the same, but each time the proof we have to derive, they are not so similar. Like the proof of the properties are not so similar. And even for, like, for example, the result we have for Heli. Heli is a subclass of weakly modular graph. We have a local to global characterization of weakly modular graph. But to prove the result we want for Heli, we have to redo another proof, because we cannot just specialize the proof we had by adding some properties. So it's maybe, but we are not smart enough yet to understand how to